Contamination, rough surfaces, and interfacial voids, because if you don't get rid of all the voids, those are going to basically make the whole thing unzip like a perforated piece of paper. Will limit the strength of many joints. We didn't really talk about this last time, but liquids are often used to overcome the surface roughness problem. I've got these rough surfaces on an atomic scale, and if I have a liquid, I can basically get rid of that there. I don't have to worry about the rough surface if I have a liquid in between. That gives me full area of contact. And we're going to see that basically adhesive bonding, soldering, brazing, and even fusion welding all essentially solve the roughness problem by interposing a liquid between the two surfaces that we want to join. In one case, in fusion welding, you actually melt the surfaces to interpose the liquid. Interfacial shear, we mentioned, was required for mechanically produced joints. If you just squeeze down on something, you only get 1/3 contact area. And then you've got 2/3 void, so that's not a very strong joint. If you slide, such as in a friction weld, and here I passed around before, this friction weld. Friction weld, you'll actually see a videotape of it sometime next week probably. Next Monday is a holiday. I'll be here Tuesday, and then I'm gone the next 2 days, but we'll have videos those days. Those are the videos some of the videos I expected you to see, and then I'll be back that Friday. But in any case, one thing's held constant, or stationary, and the other one is spun up to, in this case, it might be a couple thousand RPM, and you squeeze the two together, and just by sliding friction, this thing will start to glow red. With axial force pressed against it, you'll basically, the hot stuff in the middle within just a couple of seconds of sliding will heat up, and you'll squeeze everything out by that force. You're basically forging the thing together by using the frictional heating. And then you end up with this stuff, which are kind of little mushroomed ends, and you can machine that off if you like. You can do this with tubular joints. I think I mentioned that the universal joints on the drive shaft of most automobiles are put on. You hold the universal joint stationary, you spin the shaft, tubular shaft in that case, and then you machine it to keep it clean, make it look neat. And it's very fast. In a couple of seconds, you can make a very high reliability joint. It's also used by Pratt & Whitney and General Electric and Rolls-Royce to take $30,000 titanium parts and squeeze them together. These are discs for jet engines, and essentially weld them together. The problem there is, if you mess up the weld, you just ended up with two $30,000 pieces of scrap rather than a $70,000 completed part. Right? But it is a very fast, very reliable process. In the case of making jet engine discs, they've obviously spent the time and worked it out. Very high reliability way to join things together. We talked about the lane mirror. Contact area under normal loading never gives you more than about 1/3 of the apparent area of contact. The true area of contact is always less, and we talked about that or something. Okay. Any questions on that?
Yeah. When you do that cold welding procedure, is that joint similar in strength to the material, the base material itself?
Depends on the material. On a piece of steel like this, if it's a heat-treatable steel, it could be either stronger or weaker. If you design the steel properly, it can be stronger, just as strong. If you did a piece of heat-treated aluminum alloy, it wouldn't work, okay? Because the heat is going to destroy the good precipitation heat treatment from the aluminum. Titanium alloys is probably a little stronger in general, in most cases, because you get very rapid cooling. When you stop the process, you heat the whole thing up in 2 seconds, and you stop it, the cold metal on either side sucks the heat out, so you get a rapid cooling, more rapid cooling than you often do in fabricating the part the first time. Usually, rapid cooling of hot metal usually gives a very fine microstructure and good properties, usually. But you'd have to ask me a specific alloy before I could tell you for sure. But generally, it's in steels. That's actually an advantage of steels. It's not that difficult in steels most steels to match the strength of the weld to the strength of the base material. In fact, in low strength steels, there's actually, it's not really a problem, but it's hard to get a weld metal that is as soft as a low strength steel. And the reason for that is the high cooling rate of the weld metal. It's about 1 to 2 orders of magnitude, if not in some cases 3 orders of magnitude, faster than the cooling of the original casting or rolled structure or whatever. And so the weld metal microstructure is much, much finer, and finer usually in steels in particular means stronger and tougher. So welds are actually better. Same thing in titanium alloys, or well, not all titanium alloys, but for instance, the workhorse titanium alloys, titanium 6 aluminum 4 vanadium, invented over here at Watertown Arsenal about mid-1950s. Watertown Arsenal is now a mall, but used to be an Army arsenal. That particular alloy, when it cools rapidly, gives you a very fine, what they call basket weave structure rather than a laminar structure. So you actually have the structure kind of interlocked with itself on a very fine scale, and you actually get much better properties. Okay. In fact, at one time we had a project to essentially lay down weld metal to build up discs, big discs, by just going around and around and around. Other people try this too, but it works if you have the right type of heat source. You can end up with very, very fine structure and excellent properties. Sometimes, well, it depends on the property, but you can get a significant improvement in properties. It's not a cheap process because you're laying down metal at anywhere from, well, the old heat sources at maybe 5 pounds an hour to the modern heat sources maybe 100 pounds an hour. But one of the ideas, if you're interested, if you know 3D printing and rapid prototyping, where you try to laminated object manufacturing, they call it some of these things, you just lay the metal down. The idea is if you needed a spare part, the great big casting for a ship valve or something like that might take a year to procure, just because the foundry's backed up and they have to have the molds and everything. If you just had a diskette and you had about a $10 million facility, you could basically just put that diskette in and the thing would just lay down metal, a little bit at a time. But even if it's 100 pounds an hour, you run for, you get a ton a day, right? So in 10 days you could have a 10-ton casting, which is almost near net shape. That was the idea, and it works. If anybody wants to invest $10 million, it's not clear that investing $10 million in a capital facility that's only going to produce 1 part a week is very effective unless you can justify that it costs them other things.
Charge a pretty high price for that valve?
Well, but if you're making jet engine discs that are $70,000 and you can make one of those, you can make several of those a day. And we actually have it up to 500 pounds an hour. Now you're talking about being able to do things. And in fact, the advantage of the process we were working on was the reason most people can only lay down 5 or 10 pounds an hour is the thermal conductivity limitation. You got to suck the heat out of the part, and first you have to put it in, then you have to suck it out. But by using very high power electron beams, you actually can overcome some of those things because you don't have just surface heating. You actually can penetrate the heat down into the part, so you don't have to wait for the heat to diffuse it. You actually can deposit it several millimeters beneath the surface, and so you can put down metal much faster. However, you do have problems. You have to have 3-foot thick walls, concrete walls, because the X-rays coming off this and little problems like that. Actually, it grew out of a project. The Navy, or Defense Advanced Research Projects Agency, had a $250 million program in the 80s to try to develop particle beam weapons. These were electron beams that were going to be shot out. So if you've got a cruise missile coming in to blow up a ship, you have this electron beam and you just shoot it right through the atmosphere 30 miles away and blow up this, it's kind of the same type of missile defense people are talking about now, but this is short range, within about 30 miles of the target. And they could generate these beams. The problem was the physicists who were working on it, you've got atmospheric pressure. How do you shoot electrons through the air? It turns out they said, well, theoretically, the beam actually heats the air and causes the air to rarefied and kind of can drill a hole through the air. These things are so powerful. There's tens of megawatts of power. The only problem is there's something called a hose instability, H-O-S-E, just like a garden hose. If you have a garden hose that you know, it's just loose, it just flips around with the fluid coming out of it, and so it forms all these healable distortions. And so the only problem is you have to have a missile that's willing to run into your beam, because your beam can't hit it, you know, you can't aim it. They can get about 30 inches of a straight beam in their test. That's what they learned for $500 million or whatever. And afterwards they went and decided, well, we can't use it, the physicists decided, can't use it for shooting down missiles, maybe we can use it for welding. So I came in for a couple of days and said, well, you could melt the submarine with 10 megawatts. Okay, surface energies. Let's go back to talk a little bit about surface energies. Typical surface energy of metals is going to be on the order of 1 to 1.5 joules per meter squared. For a ceramic, it's going to be on the order of 0.5 joules per meter squared. For a polymer, it's going to be on the order of 0.1 joules per meter squared. And actually, it's going to be 0.02. Okay, now this actually is, if you want units that I prefer to use, these would be like 1,000 to 1,500 ergs per square centimeter. That's the surface energy. The surface tension would be dynes per centimeter. But in any case, metals have much higher surface energy than ceramics, which are typically ionically or covalently bonded, and much higher than polymers. Anybody know why? Or why are ceramics different than polymers in terms of surface energy? What type of bonding do you have holding those chains together in a polymer? It's van der Waals. So van der Waals bonding is significantly weaker than the primary bonds that are holding the ceramic structure, and the ceramic structure can be either covalent or ionic, but the van der Waals bonds are about 1/5 as strong as the ionic or covalent bonds, and so the unsatisfied bonds on the surface of a polymer are basically unsatisfied van der Waals bonds. Therefore, the unsatisfied surface energy is much lower in a polymer than it is in a ceramic. However, a metal can be 2 to 3 times higher than either covalent or ionic bonding. You might have an idea why that is. How local? Well, let me back up. Covalent bonding is very localized between 2 atoms, right? You're sharing an electron between just 2 atoms. Ionic bonding is also very localized, in a sense. You're sharing a charge transfer between 2 atoms. And the charge transfer interaction effect dies off as the radius squared. So you go 2 atomic distance away, and it's only 25% of what it was. Okay? Now in a metal, the outer shell electrons in a metal are free to move around anywhere in the metal they want, and therefore it turns out in the metal, the electrons that are participating in the bonding can actually be felt 2, 3, 4 atomic distances away. And so, if I draw myself a little model of the surface, this is very simplified, but it's conceptually correct, okay? And this is my bulk solid, and these are my unsatisfied bonds on the surface. Well, for a ceramic, basically the surface energy comes from covalent and ionic bonding from the top monolayer or 2 of atoms near the surface. For a metal, on the other hand, essentially, I'm going to have electrons way down deep in the metal that participate or would have satisfied, if you will, some of these bonds on the surface. And since they're not completely satisfied, there's not another atom to kind of balance their charge in the way the structure wants to, you'll end up with a lot more surface energy, because the surface energy ultimately is the energy of the electrons and how satisfied they are, whether they're actually chemically bonded to another atom. Because of the longer range distance of bonding in a metal, or the movement of the electrons in a metal, metals have unusually high surface energy compared to other materials. That means that metals, in principle, will be very good at sucking up contamination from the air, whether it's grease molecules in the air, or CO2, or oxygen. Why do we have metal catalysts in chemical processing plants? Because those metal surfaces are very, very active. They have a lot of surface energy. They can do a lot of work on those electrons that are changing the bonds. So why do you have a palladium or platinum catalyst in your car? Why isn't it a ceramic catalyst? It might have a ceramic support, but it's active metal on the surface. And why is it palladium or platinum? Because they don't form a surface oxide. So you actually have potentially the metal available, and if you heat the catalyst up to a high enough temperature, you can actually get the sticking fraction. The ones that hit, a certain fraction of them are going to go away, and you can get things come down, react, and then go away. Right? So so metals are easy to bond if you can get rid of the contamination. Ceramics are a little bit more difficult to bond, and polymers get to be a pain in the neck to bond by adhesive bonding. And in fact, if you want to keep something from bonding, you typically put some sort of oil, which is a polymer bond, right, on the surface, right? If I had a piece of oily Scotch tape, it doesn't work, right? And that's because I've contaminated the surface of the Scotch tape with oil, which has a low surface energy. In order to get two things to stick together, if I take two things with a high surface energy and stick them together, they create a low interfacial energy. That means they lowered their energy and they'll bond. If I take two things with a low surface energy and try to stick them together, unless they can lower their surface energy even further, they won't stick. And so Teflon is one of the most difficult things to bond to. When we get to adhesive bonding tomorrow or whatever, we'll talk about tricks to bond Teflon. But we did talk about how to make Teflon pops, right? And that's a mechanical interlocking. And it turns out there's another way to do it too. But it turns out another form of mechanical interlocking. One of your handouts has surfaces and interfaces, and it has the interfacial energy. Water, which is a covalently bonded molecule, right, H2O, has a surface energy of 72 ergs per square centimeter, 0.07 joules. Okay, it's hydrogen bonded. So this is actually hydrogen bonded, and this is non-polar van der Waals type of bonding down here at 0.02. Teflon has a surface energy of about 20. And I think you've been given a handout on that. Copper has got surface energy of 1.4 joules. If I look on here, aluminum oxide solid has 900. Now it turns out aluminum oxide is a covalently bonded solid, and it's on the high side, so I could have given you a range on this. But let's see, it's got calcium chloride is 0.45. So it varies by a factor of 2 within a given classification typically, but it is, those are the kind of orders of magnitude. That becomes important both in adhesive bonding and also in soldering and brazing, is what the surface energies are. Any questions? Any of that? The other thing, to get back to the question that was a little bit earlier, someone asked about in the gold thermocompression bonding, we basically took a gold wire and we squeezed it into a surface and we made a pad that may be 3 or 4 times the diameter of the wire. And my interfacial shear here is when I squeeze this into the surface. I start out with a wire like this, and actually the little wires in some cases, I may melt a little rounded blob on the end with a little arc when I cut the wire off and push that little rounded melted piece into the surface, and it spreads out. And this is approximately what it'll look like. It turns out I won't get a very good bond right in here. Why? Because it's straight normal force. Sometimes my better bond is going to be in the intermediate regions in here. I don't have any sliding there. But where it first comes down in contacts, I may not get very much sliding. It's kind of a stagnation point, if you will, right? So I actually kind of get a donut-shaped bond because my maximum shear is going to be out away from R is equal to 0, the radius is equal to 0, right? There's essentially a stagnation point for the flow here, and there's no sliding there. Now, there's also ultrasonic welding. Ultrasonic welding, typically you take a machine that has a vibrating horn, it looks something like this. And on the end of this, you'll have a little probe, and down here at the bottom, you'll have your parts that you want to join together. So here are my parts I want to join together, and I apply a downward force here, and on this thing, I oscillate it ultrasonically, maybe 100 kilohertz, something on that order. It's hard to vibrate something mechanically at much higher frequencies and get very much displacement, because the energy is the force times the displacement, right? But you could use 20 kilohertz. They call it ultrasonic because it's above 20 kilohertz, right? But 20 to 100 kilohertz is typical type of bonding frequency for ultrasonic welding. In ultrasonic welding, I essentially have a small displacement oscillating back and forth. So it's not like thermocompression bonding where I rub the thing, or friction where I got big shears. Here I have little microscopic shears. So what happens to the contamination in that friction weld I pass around? You squeeze the contamination all the way out, right? Where does the contamination go when I do this? It stays there, okay? And in fact, you end up with, maybe in most cases, no more than 50% bonded area, because I'm going to have little islands of oxide or other contamination that are left behind because I never did something that extruded things all the way out. Now, it turns out at Sandia National Labs once, they showed me that they actually, for some part of the nuclear warhead or whatever, they had this probe here had like an 8-inch radius. It's not good. The probe was probably smaller than that, but they put a very, very shallow radius on this, and then squeezed the plates together. They wanted to ultrasonically weld and increase the force over time, such that initially you had contact at one point and it was vibrating, and you kept on increasing the force, and so the contact area starts spreading out radially. And what they were doing is they were essentially pushing a wave of oxide out, and they could get much stronger bonds. Maybe they only had 20 or 30% oxide contamination. Very expensive process to do this. Just to machine these things was not cheap. But the advantage of ultrasonic welding, you can weld things like aluminum with a heavy oxide together. You can weld copper, and you don't end up deforming the substrates because you're just doing slight interfacial friction. So there are tricks people do, but in general, I don't care for ultrasonic welding because most commercial ultrasonic welding just buries the contamination. It doesn't eliminate the contamination. So about the best you ever get is a 50% joint. Ultrasonic welding is probably most commonly used on plastics. It works pretty well on plastics. Why? Well, one of the reasons is plastics have low thermal diffusivity. So you can really localize the frictional heat. The frictional heat is generated at the interface, and since the plastics don't conduct the heat away, it doesn't take as much energy to do this. Now, I didn't mention, I drew the horn, the thing is vibrating like this. A big cylinder here, tapering down with a big radius to avoiding stress concentrations, to a smaller horn. Anybody know why you do that? If this is what's being driven by whatever my displacement thing is, I have a force times a distance, if you will, right? And over this whole volume, if I taper down here, those stress waves in this solid, I'm transmitting the same energy, but over a smaller volume, I actually can increase the effective displacement. It's a way to magnify a stress wave in a solid to taper it down. So basically that's why the horns on, what they call horns on ultrasonic welders, well, they call them horns because look at it. I mean, if it were hollow and you blew it this way, it has the shape of a tuba or a trumpet, right? So they call it a horn because of its shape. It has that flaring shape backwards or tapering forwards because you're trying to take a fairly diffuse vibrational energy and concentrate it at a spot. Okay, so you can magnify it down to a spot like that. Now, the last thing we can talk about is, we talked about rotational friction welding, and I showed you the first day a plate of aluminum that was friction stir welded. In friction stir welding, you put two plates together and you take a rod that you rotate the rod so the plates are stationary, and you stir the rod. You're basically stirring the two pieces together. It's good for aluminum. People are trying it on titanium. The problem is the rod is supposed to be non-consumable, and it's got to remain hard and not deform, or otherwise you're not putting energy into the part. And so for aluminum, you can basically use steel rods, or stainless steel, or whatever. But you go to higher melting materials, like titanium, and the rod material has to be some refractory material like tungsten or molybdenum. I heard a talk by a professor once. He told all about friction stir welding a couple of years ago of titanium, and everybody said, well, what did you use for your stir rod? He says, well, that's proprietary. Well, it's proprietary, but if you think about what material properties you need good thermal diffusivity to carry the heat away, and you need a high melting temperature, and that turns out that's going to be molybdenum. Okay? But, you know, he's already patented. But, I mean, it's not too hard to figure out. I mean, I don't know. He didn't tell me what it was, but I'd be willing to bet anybody in the room that it was molybdenum. Okay? Just because I know what the thermal diffusivity of the refractory metals are. And molybdenum is much higher than any of the others. But you're limited by what your stir rod is. You're also limited, well, friction stir welding is very good on aluminum. Doesn't create distortion. It's not clear that it's much good for anything else, although they're touting it for all kinds of things. Another type of friction welding is called linear friction welding. And if you have, one of the things the Air Force has spent millions of dollars on this, and I've mentioned before a couple of times already, trying to take weight off a turbine disc. And I didn't bring the turbine blade with me, but you've seen turbine blades, and the turbine blade has an airfoil section, and then it has this kind of big flange section down here, and then it has what they call the Christmas tree structure underneath. And that Christmas tree structure is a mechanical interlock. And this flange down here, this is the working part, that's the airfoil, it's got the curved surface, right? This flange and this Christmas tree structure are basically there just to take the stresses of this thing being attached to the disc and the centrifugal forces as this thing's rotating around. And those are pretty significant forces. But any type of mechanically fastened joint, whether it's a bolted joint or a flange joint, is very heavy. You have to have lots of metal there because the mechanical joint's not as strong per unit area as an actual weld. And so there's a lot of excess weight in that flange at the bottom of the turbine and on the disc. If you could weld the airfoil, the curved section, directly to the disc, you can get rid of this flange and you can eliminate 20 pounds per disc. And so they've been looking for several years at linear friction welding. How do you weld these nickel-based superalloys to the disc? So you got this round disc that you want to put these blades on, these airfoils. And so basically you can feel friction welding if you just rub your hands together, right? That's linear friction welding. It gets warm when I do this. Okay? I can feel the heat in my hand. They do this in a great big machine, apply a downward force, and then they slide the two back together and you can make a weld. The problem is if I have to put 200 blades at $4,000 a piece on top of a disc that costs $30,000, and every one of them has to be good, the scrap costs are horrendous because I can't do it. There's not a good repair procedure for it. They call this a blisk for bladed disc if they can do it. Okay. And the reason the Air Force wants to do it is you can eliminate 20 pounds of flange per disc, 200 pounds per engine, 2,000 pounds per fighter. 2,000 pounds of fuel per fighter. I don't know if that's another hour's worth of mission, or it's another 2 bombs or 10 bombs, depending on the type, or missiles or whatever it is you're carrying. It'd be big payload advantage.
Is there any good way to break one of those welds once you have it? If you have to with it to replace the blade?
Well, you can machine them off. I mean, you at the price, the value of that bladed disc, you could afford to machine it off and put a new one on. The problem is, what damage have you done? You know, are you going to have to do some buildup of the bottom part? And you know, frankly, I don't know all the real problem is the repair, okay, and getting consistent welds every time. You can make welds, and you can certainly make a weld or maybe even 10 welds that are all very good. But they haven't gotten it to a reliable enough. They haven't given up on the program because the payoff here is tremendous. Those of you that are in the other part of the course know that on an aircraft, 200, over the life of an aircraft, each pound is worth $200. On a fighter aircraft, it might be $1,000. So if you're talking about 2,000 pounds, you're talking about $2 million savings per aircraft if you can do this. That could be significant. I mean, they may cost $50 million a piece now anyway, but even so, you know, getting a 4% savings on a $50 million object is enough for some people to retire on. Okay, thanks. See you tomorrow.